Hi, I'm Carl Host from the Lincoln Electric Welding School, and I'd like to welcome you to another master class from ARC Magazine. Today we're going to be talking about some tips and tricks on welding titanium. Titanium has only been used commercially since about the late 1940s, early 1950s, and it was started out with heavy use in the aerospace industry, but in recent years it's seen use in a lot of other industries, including motorsports. One of the benefits of titanium is it's lightweight. It weighs about half the weight of steel, but yet it has strength very similar to steel. So a piece of titanium, like what I have in my hand here, is 3/8 of an inch thick and about 1 foot long, and I have a piece of steel about 3/8 of an inch and 1 foot long. This weighs 1 3/4 pounds. This weighs 3 3/4 pounds. Similar strength. So that's a big difference in strength to weight ratio. But it also has excellent corrosion resistance in salt water, impervious to salt water, so it's used a lot for condensers and desalination of salt water, heat exchangers, all different industries use it. I brought in a motorsports part here. This is actually an exhaust system. Not too often is it used for exhaust systems because it's good up to about 1100 degrees Fahrenheit service temperatures, but these exhausts on motorcycles are sometimes operate below that temperature, so they can be used, and it does save a significant amount of weight for a piece like this. This part I was going to repair today, but chose not to because it's going to take a little more time to do than what we wanted to do here, but this had some damage done to it, as you can see here. And if I was going to repair this part, it would require me to purge the inside and also use a large flooding cup on the outside. It would be kind of hard to use a trailing cup in this situation. These parts would have to be cut away to get access back in here, and we would also have to remove the oxide off the surface of this. This part has been used, and you can see that blue oxide coating, and that means the surface of the titanium is enriched with oxygen. So we would want to strip that off or machine that or sand that off, etch it off, and get that clean before we started to weld. I would also want to remove this area that's damaged and get up underneath and clean that as thoroughly as possible as well. So this part would require a little work before we can work on it. One of the important things with titanium is it is hardened from oxygen, nitrogen, carbon, and other elements. But oxygen is one of the primary hardening agents, and that's in our air we breathe. So it's very important that the titanium is thoroughly shielded during welding and also after welding. We use sometimes trailing cups to trail behind us as we're welding to keep the titanium covered until it cools down. They have different types of trailing cups here. And you also would have your backing gas, which could go on the back side of something. Say I was welding on one side of this plate, I would also want to protect the back side of the plate as well. Any part of the titanium that's exposed to oxygen or nitrogen in the air could become hardened and brittle. Also very important that we keep it shielded during welding. During welding, I'm going to use a large jumbo cup. This is over 1 inch thick inside diameter. It's a Pyrex type cup, gas lens shielding. A little higher gas flow than usual. I'm going to run around 30 on my gas flow, 30 cubic feet per hour. And it's important to have excellent clean gas while we weld, pure gas. Always check your hoses, make sure there's no leaks in the hoses, make sure the hoses are designed for inner shielding gas so that they don't add contaminants to the gas, such as moisture, so special gas hoses for titanium welding. People that do high-end titanium work in the aerospace industry actually purchase special gas that has been tested to make sure that the oxygen levels and hydrogen levels are very low in the gas and it has a low moisture content. That's all very important with titanium welding. Today the grade we're going to weld on is 35 thousandths thick, and it's a commercially pure titanium. That's the particular grade. It's called CP2. It has small amounts of oxygen added to it for strength. Typically, this grade is selected for applications where corrosion resistance and ductility is more important than strength, structural strength. About 20% of the titanium production today is on commercially pure titanium. The other 20% is used on the alpha-beta grades like the 6 aluminum, 4 vanadium grades. And that is a higher strength grade, and that's primarily used in aerospace. So I'm going to set this up in a purge block. What I want to do is purge the underside and protect it. And I'm going to stick with just a big jumbo flooding cup on the top. That's going to be my primary gas. This will be my back gas. I'm going to avoid a trailing cup at this time. So I'll set these up into the purge block and we'll get started. Today we're going to be welding with an Aspect 375. This is a higher end TIG machine. It would be used in aerospace and advanced motorsports, welding, that kind of industry. So let's go over and turn this machine on. I'll show you a couple of settings that I would use with this machine. First, we'll put the power on. It'll take a second to boot up. Okay, the straight lines tell you I'm going to be on DC negative polarity. That's the polarity that I'm going to use today for titanium welding. I am using a high frequency start to start the arc so that I don't have to touch the tungsten to the work, which could possibly contaminate the titanium. I'm using a two-step control. Now I'm going to go in and check a few things on the inside here. And it says my end current post-flow time is set for 18 seconds. I'm going to leave that up. It's kind of high for the amperage I'm running, but I'm going to leave it up higher to keep that argon on after I'm done welding. There's also a pre-flow time, and I've got that already turned up to about 1 second. I'm going to give it a little extra gas ahead of time because I'm using a really big cup and I kind of want to flood the area with gas before the arc starts. And we got starting current, says 40 amps. Now, that's something I don't like, and with this machine, I'm running a 1/16 tungsten. The default start on this is for 332 tungsten. So what I'm going to do is go to the internal menu, hold this in for a couple seconds, about 5 seconds, I believe, and you'll see I'm on the internal menu, and where I flashed over the diameter of tungsten, 332, I'm turning it all the way down to 20 thousandths. I know I'm going to use a 1/16 tungsten today, but I want to be able to turn it down even lower because I don't want to blow through this thin material. So I'm going to exit out, and now when I go to my starting menu, it's starting at 5 amps, and it'll actually go down to 2, but with a 1/16 tungsten, it'll start pretty good about 5. I'm going to exit out and leave it there. That'll give me a really nice ideal start with this machine. So I have I got a 1 second pre-flow, a 5 amp start, and a post-flow of 18 seconds. I'm running about 30 cubic feet per hour on my argon flow, on my primary flow, my primary gas. On my backing gas, I'm running 10 cubic feet per hour in this special purge block. I'm using I believe it's an 1/16 cup. That would be a number 16. And it's a Pyrex cup. Not a lot of stick out on the tungsten. I only have it sticking out maybe half an inch, but the big cup, that should be okay. 30, 40 amps. I'm guessing this titanium is about 35 thousandths thick. I have the machine set for 40. I may back off of that just a little bit as I'm welding. I'll probably run around 35 to 37 amps as I weld. I'm going to make a tack first. Always make sure I keep the gas on until it cools down. I also keep the end of the wire under the gas at all times. You do not want to remove the wire from the gas and expose the hot wire to oxygen. In some cases, I would use a trailing cup, but today I'm not going to use a trailing cup. I'm using this large gas lens, and because I'm down in this trough, the argon kind of floods that area, and I think I'll be able to get a color-free weld without using a trailing cup. Start at the beginning and weld right through. This will be a full penetration butt weld. Puddle's nice and clear. Have to be careful not to get that wire out from underneath that shielding. Also, if the wire comes out of the puddle a little bit, it does tend to stick more than regular stainless steel or steel. The titanium has a little lower melting temperature, so the molten metal on the end of that wire freezes pretty quick. And it really will stick if you get it outside of that weld puddle. Sometimes this thin material can be welded without filler. I probably could have just as well done this without filler. But I'm using a 0.45 diameter commercially pure 2 filler wire. Keep the gas on the wire. Till it cools down. And it looks like we have a pretty good color-free weld here. Okay, this titanium looks like it did pretty good on the color inspection. The top surface where I welded is silver, and also the back side, the back purge is silver. There's no color in there. A little bit of color further away from the weld is okay. It's acceptable to have color within a 32nd of an inch from the edge of the weld. And I'm quite a bit of ways before you see any color at all. So when they inspect titanium, they use comparators. So let's look at this titanium inspection kit that we have here. As you can see, there's a series of plates, and the top one up here is silver, which is a perfect weld. The second one is kind of a light straw colored, or like a light straw colored, or almost gold, and that's also considered acceptable. As the colors get darker, like dark straw to blue, purple, even yellow, all the way up to a white, which is kind of a chalky white, that is severely contaminated here. So the more oxygen that was absorbed into the surface at high temperatures, the darker the oxide layer is. And that's an indicator of oxygen being absorbed into the surface. Okay, so as you can see, the color is pretty good here. Now, if the titanium gets exposed to heat after welding by not using a trailing cup and there's discoloration, chances are it didn't hurt the weld that much as long as there was good shielding during the weld. But the inspector that inspects titanium welds doesn't know how it got exposed. So if they see blue or dark golds or blues or purples or white, the part is rejected. Any part that is not purged on the inside, like a structural component, if there's not argon inside, like a bicycle frame, that will severely embrittle the titanium. So any titanium that's heated above 800 degrees during welding should be protected from the air we breathe. And that also means cleanliness is very important. To wipe the parts down clean before welding, use acetone with safe procedures, safe gloves, and when you're handling acetone, be careful with that. But wipe the parts down with acetone, remove any oil from fingerprints, generally separate titanium from other operations, clean gloves that have only been handling the clean titanium. That's all important stuff. That'll do it for another ARC Magazine Masterclass. I'm Carl Hose. Thank you for watching.